Something is moving through our solar system right now, and the odds of what it is doing are so astronomically small that it forces us to ask questions we may not want to answer. In the past 72 hours, Professor Avi Loeb has updated his list of anomalies surrounding 3I Atlas to 10 distinct impossibilities, each one stacking on top of the other like evidence in a trial where the defendant might not even be from this world. Today, we are going to walk through every single one of these anomalies, not as speculation, but as documented scientific observation, and by the time we reach the 10th, you will understand why some of the brightest minds on this planet are no longer comfortable with simple explanations. If you find value in what we uncover here, please take a moment to like this video and subscribe to the channel. Your support helps us continue bringing you the latest developments on 3I Atlas as they unfold in real time. And tell me in the comments, where are you listening from, what time is it there, and which of these 10 anomalies do you find most compelling as evidence of something beyond natural origin? The ecliptic alignment, a 1 in 500 chance. When 3I Atlas was first detected on July 1st, 2025, astronomers immediately noticed something peculiar about its trajectory. This was not just another object passing through our solar system at some random angle. This interstellar visitor, travelling from beyond our cosmic neighbourhood at over 130,000 miles per hour, was moving along a path that aligned almost perfectly with the ecliptic plane, the flat disk where all of our planets orbit the Sun. Think about that for a moment. The ecliptic plane is essentially the solar system's highway, a thin band of space where Earth, Mars, Venus, Jupiter, and all the other planets circle our star. It represents a tiny fraction of the three-dimensional sphere of possible approach angles an interstellar object could take. Imagine a basketball representing all the possible directions something could enter our solar system from. The ecliptic plane would be a piece of paper lying across the middle of that basketball, maybe a few millimeters thick. The chances of randomly hitting that paper when throwing a dart from across the room are vanishingly small. To understand just how remarkable this alignment is, we need to step back and consider the geometry of interstellar space. Our solar system sits in the Orion arm of the Milky Way galaxy, surrounded by hundreds of billions of stars scattered across three-dimensional space. When an object is ejected from another star system, perhaps during planetary formation, or through gravitational interactions, it begins a journey that could last millions or even billions of years. During this time, it is buffeted by stellar winds, pulled by the gravity of passing stars, and influenced by the complex gravitational field of the galaxy itself. The result is that interstellar objects should arrive at our solar system from essentially random directions. There is no preferred orientation, no cosmic arrow pointing them toward our ecliptic plane, and yet 3I Atlas arrived within 5 degrees of that plane, travelling in retrograde. The precision is startling. Professor Loeb calculated the statistical probability. 3I Atlas arrived within 5 degrees of alignment with the ecliptic plane. The odds of this happening by pure chance, 0.2%, 1 in 500. Put another way, if 500 interstellar objects randomly entered our solar system, only one would naturally align this closely with where our planets live. To appreciate what this number really means, consider that professional astronomers work with probabilities every day. When they discover an exoplanet, they calculate the likelihood that their signal is real versus instrumental noise. When they detect gravitational waves, they compute the probability that the pattern matches their theoretical models. A 0.2% probability is not quite at the gold standard threshold of 5 sigma, used in particle physics, but it is well within the range where scientists take notice and demand explanation. In astronomy, when we encounter something with a 1 in 500 chance of occurring naturally, we do not simply shrug and move on. We investigate. We look for mechanisms. We ask whether our assumptions about randomness are correct. And in the case of 3I Atlas, the more we investigate, the more questions emerge. The calculation itself is elegant in its simplicity. Take the total solid angle of the celestial sphere, that is, all possible directions from which an object can approach. Now calculate what fraction of that sphere corresponds to trajectories within 5 degrees of the ecliptic plane. The ratio gives you the probability. It is basic geometry, but the implications are profound. But here is where it gets interesting. 3i Atlas is not just aligned with the ecliptic, it is travelling in retrograde, meaning it is moving in the opposite direction to the planets. Most objects in our solar system orbit the Sun in the same direction because they formed from the same rotating disk of gas and dust billions of years ago. Retrograde orbits are rarer, accounting for a small fraction of solar system bodies. For an interstellar visitor to arrive in retrograde and still align so precisely with the ecliptic plane reduces the probability even further. Some might argue that this is simply coincidence, that we are reading meaning into randomness the way humans see faces in clouds. But probability is not opinion, it is mathematics. When Professor Loeb presents a 0.2% likelihood, he is not guessing. This number comes from modelling the distribution of stellar velocities in our galactic neighbourhood, understanding the three-dimensional geometry of interstellar space, and calculating how many approach vectors would produce the observed trajectory. The implications become more unsettling when you consider what an ecliptic alignment would mean for a technological object. If you were designing a probe to study a solar system, to observe its planets, to potentially interact with them, you would want to travel along the plane where those planets exist. You would not waste energy diving steeply above or below the system. You would not risk missing your targets. You would align your trajectory with the ecliptic plane because that is where the interesting things are. That is where life is most likely to exist. That is where Earth is. In November 2025, Professor Loeb published updated calculations showing that 3i Atlas passed remarkably close to Mars, Venus and Jupiter during its inbound journey. These were not abstract near misses in the vastness of space. The object came within tens of millions of kilometres of these worlds, close enough that a spacecraft could easily perform observations or deploy smaller probes. The timing of these encounters was not random scattering. It was sequential. It was methodical. Let us be specific about these encounters because the details matter. On October 3rd, 2025, 3i Atlas passed approximately 30 million kilometres from Mars. This is roughly 80 times the distance between Earth and our Moon, close enough that the European Space Agency's Mars Express and ExoMars Trace Gas Orbiter were able to capture images of the object as it sailed past the red planet. Then, just days later, 3i Atlas approached Venus at a distance that would have placed it well within reach of any orbiting spacecraft. Had Venus not conveniently lost its primary observer just before the encounter? The Venus situation deserves its own examination. On October the 28th, 2025, one day before 3i Atlas reached perihelion, the Japan Aerospace Exploration Agency announced that the Akatsuki Venus orbiter, which had been silent since April 2024, was officially dead. The timing raised eyebrows across the astronomical community. Why announce the death of a spacecraft 17 months after losing contact? And why do it precisely when the most anomalous interstellar object in history is about to pass nearby? We will return to this question in later chapters, but for now, note the pattern. 3i Atlas trajectory brought it near multiple planets, and at the most critical observation window, our eyes at Venus went dark. Jupiter is next on the object's itinerary. On March 16th, 2026, 3i Atlas will pass within 54 million kilometres of the gas giant. Well positioned for observation by NASA's Juno spacecraft if the mission chooses to redirect its instruments. The fact that 3i Atlas will have close encounters with Mars, Venus, Earth and Jupiter, the 4 most interesting planets in our solar system for very different reasons, strains the boundaries of coincidence. Amateur astronomers around the world have been tracking 3i Atlas with increasing intensity since perihelion on October 29th. The data they are collecting independently confirms what professional observatories are seeing. The retrograde ecliptic trajectory is real. It is measurable. It is happening. What makes this even more statistically significant is that 3I Atlas is only the third confirmed interstellar object we have ever detected. The first, 1I Oumuamua, arrived from a completely different angle, plunging through the solar system at a steep inclination. The second, 2I Borisov, also approached from well outside the ecliptic plane. 3 detected interstellar objects, 3 different origins, and only one of them threaded the needle to align with our planetary highway. If interstellar objects arrive randomly from all directions across the galaxy, we should not have seen an ecliptic-aligned visitor this soon. The statistics say it should be far more rare. Some scientists have proposed that the Milky Way's galactic disk could create a bias in interstellar object trajectories, that objects might preferentially travel along certain planes due to the distribution of stars. But even accounting for this galactic structure, the precision of 3I Atlas alignment remains an outlier. The galaxy is not so ordered that every interstellar traveller automatically knows where our ecliptic plane is located. There is another consideration that rarely gets discussed in academic papers, but deserves attention. If 3I Atlas is a natural comet ejected from another star system billions of years ago, its trajectory has been influenced by countless gravitational interactions during its journey across interstellar space. Every close pass by another star, every interaction with molecular clouds, every tiny perturbation from the galactic gravitational field would have altered its path. The likelihood that all of these random influences would conspire to deliver 3I Atlas precisely into our ecliptic plane approach is zero. It is like flipping a coin 500 times and having it land on edge. Professor Loeb has been careful to emphasise that he is not claiming 3I Atlas is definitely artificial. He assigns a 30 to 40% probability that the object does not have a fully natural origin. But he also points out that in science, we must follow the data wherever it leads, even if it makes us uncomfortable. The ecliptic alignment is data. The 0.2% probability is data. We cannot ignore it because the implications are unsettling. In the past week, several astronomers have published rebuttals suggesting that 3I Atlas trajectory is not as unusual as Loeb claims. They argue that with limited data on interstellar objects, we cannot yet know what a typical distribution looks like. This is true. We have only detected 3 such objects. But this argument cuts both ways. If we are genuinely in the dark about what is normal, then we also cannot dismiss 3I Atlas as definitively natural. We are in uncharted territory, and pretending we have certainty in either direction is intellectually dishonest. What would it mean if the ecliptic alignment is not coincidence? It would mean that something, either natural processes we do not yet understand, or an intelligence we have not yet encountered, caused 3I Atlas to arrive where it did. It would mean the object is here for a reason related to our planets, to our sun, perhaps to us. It would mean that December 19th, 2025, when 3I Atlas makes its closest approach to Earth at just 167 million miles, may be more significant than we currently imagine. The alignment also raises questions about observation. If 3I Atlas arrived along the ecliptic plane, it would have been positioned to observe our planets from an optimal angle for months before and after perihelion. Earth, Mars, Venus and Jupiter would not be tiny dots lost in the void, but prominent features moving against the backdrop of the Sun. A probe equipped with even basic sensors would have collected vast amounts of data about planetary atmospheres, magnetic fields, and the signs of technological civilization, if it knew where to look. During September and October, before 3I Atlas passed behind the Sun, multiple observatories captured images showing unusual jet activity. These jets, which we will explore in later chapters, appeared at angles consistent with directional control, not the random venting expected from a comet nucleus heating unevenly. If you wanted to make small course corrections to maintain an ecliptic trajectory, pulsing jets in specific directions would be exactly how you would do it. the retrograde aspect adds another layer of strangeness. Moving opposite to planetary motion means 3i Atlas had a longer observational window for each world it passed. Instead of rushing by in the same direction as the planet's orbit, travelling retrograde allowed the object to spend more time in proximity to Mars, to Venus, to Earth. If you were designing a flyby mission, retrograde would give you more data collection time per planetary encounter. Consider the engineering implications of a retrograde ecliptic trajectory. In our own space exploration history, missions like Voyager and New Horizons were designed to use the orbital motion of planets to their advantage, slingshotting from one world to the next by travelling in the same direction as planetary motion. But if your goal is not speed but observation, if you want to maximise the time spent near each target, retrograde makes perfect sense. You approach each planet from the opposite direction, effectively creating a longer encounter window. The relative velocity differences become crucial here. When 3i Atlas passed Mars travelling, retrograde, the closing speed between the object and the planet was much higher than it would have been for a prograde encounter. But this also means that from the object's reference frame, Mars appeared to move past more slowly against the background stars, providing a more stable observational platform. For a natural comet, this distinction is meaningless. For a probe equipped with cameras and sensors, it is everything. There is also the question of energy. Achieving a retrograde ecliptic trajectory from interstellar space is not impossible, but it requires a very specific set of initial conditions. The object must have been ejected from its parent star system with velocity and direction components that, after accounting for millions of years of gravitational perturbations from other stars and the galactic potential, result in this precise alignment when it reaches our solar system. The probability space for such a trajectory is vanishingly small. Professor Loeb recently stated in an interview that the ecliptic alignment, combined with the other 9 anomalies, has convinced him that we must take seriously the possibility of technological origin. He is not asking people to believe. He is asking them to remain open to evidence, to let observation guide conclusion rather than letting conclusion filter observation. The alignment is real. The statistics are uncomfortable, and this is only the first of 10 anomalies. What we are about to explore in the coming chapters are not wild speculations or conspiracy theories detached from reality. They are measurements, observations, peer-reviewed findings, and mathematical calculations performed by scientists at Harvard, NASA, ESA, and institutions around the world. Each anomaly stands on its own as unusual. Together, they form a pattern that is becoming increasingly difficult to explain with conventional models. But the ecliptic alignment is foundational because it speaks to intent. Random natural objects do not care where they travel. They follow physics, nothing more. They tumble through space for millions of years, arriving wherever gravity and momentum take them. But objects with purpose, whether biological or technological, choose trajectories. They aim, they align. And 3i Atlas aim directly at the plane where we live. In the days since perihelion, as 3i Atlas has begun its journey back out of the inner solar system, amateur astronomers with modest telescopes have continued tracking its path. They have confirmed what the professionals already knew. The ecliptic alignment remains precise. There has been no significant deviation, no evidence that the object is tumbling chaotically, or that its trajectory is being randomly perturbed. It moves with purpose, with precision, along a path that gives it access to the most interesting real estate in our solar system. The alignment also tells us something about timing. 3i Atlas was discovered on July 1st, 2025, but analysis of archived telescope data shows it had been photographed as early as May 8th, 2025, when its brightness was still very faint. By working backward from its current trajectory, astronomers calculated that this object has been approaching our solar system for years, possibly decades, and throughout that entire journey it maintained its ecliptic alignment. This was not a last-minute course correction. This was the plan from the beginning. Professor Loeb has repeatedly emphasized that the scientific method requires us to consider all possibilities. even uncomfortable ones. If we dismiss the ecliptic alignment as mere coincidence without thoroughly investigating it, we are not practicing science. We are practicing belief, and belief, whether in natural explanations or technological ones, has no place in rigorous inquiry. The coming months will be critical. As 3i Atlas emerges from behind the Sun and becomes visible again to ground-based telescopes, astronomers will be watching for any signs of trajectory changes, any evidence of manoeuvring, any deviations that cannot be explained by gravitational forces alone. The object's path is known with high precision now. Any departure from that path will be immediately noticeable. But for now, we are left with the undeniable fact of alignment. 0.2% probability, 1 in 500 chance. A retrograde trajectory that threads the needle through our planetary system. And this is only the beginning. Because what 3i Atlas did while travelling along that ecliptic plane is where things become truly strange. The sunward jet that defies physics. During July and August 2025, observers around the world began noticing something that should not exist. 3i Atlas was developing a tail, but this tail was pointing in the wrong direction. Instead of streaming away from the Sun as every comet tail in recorded history has done, this one pointed directly toward it. At first, astronomers assumed they were witnessing a familiar optical illusion. Comet tails can sometimes appear to point sunward due to perspective effects when Earth, the comet, and the Sun align in specific geometries. We call these anti-tails, and they have been documented dozens of times with solar system comets. They look strange, but they are perfectly explainable as projections of the normal dust tail onto our line of sight. Professor Loeb and his team immediately began checking whether 3i Atlas anti-tail could be explained by perspective. They ran the geometric calculations, modelling Earth's position relative to the comet and the Sun throughout July and August. The answer came back clear. This was not an optical illusion. The sunward jet was real. Material was actually being ejected from 3i Atlas toward the Sun, not away from it. This is where intuition breaks. Comets behave the way they do because of solar radiation pressure and the solar wind. When a comet approaches the Sun, its icy surface heats up and sublimates, turning directly from solid to gas. This gas carries dust particles with it, and both the gas and dust are then pushed away from the Sun by radiation pressure and the stream of charged particles flowing outward from our star. The result is the classic comet tail, always pointing away from the Sun regardless of the comet's direction of travel. For material to move sunward, it would need to overcome this outward pressure. It would need to be accelerated toward the Sun with enough force to fight against radiation pressure, against the solar wind, against every natural process that governs comet behaviour. In the natural world, this does not happen. There is no known mechanism for a passive ice ball to eject material sunward with sufficient velocity to create a sustained jet. The observations were not ambiguous. Multiple telescopes captured images showing a distinct plume extending from 3i Atlas nucleus toward the Sun. The morphology was different from the normal tail that also developed. This was not a broad diffuse cloud but a collimated jet, suggesting the material was being expelled from a specific location on the object's surface with directional intent. Professor Loeb published his analysis on August 15, 2025, presenting the data to the scientific community and asking for alternative explanations. Some researchers suggested that perhaps the rotation of the nucleus could create asymmetric outgassing that might, under very specific conditions, produce a sunward component. But when you run the physics, the numbers do not work. The solar wind pressure at 3i Atlas distance from the Sun during July and August was strong enough that any naturally outgassing material would have been swept away before it could establish a visible sunward jet. Think about what is required to create this effect. You need a source of material, obviously ice or gas from the comet nucleus. You need that material to be expelled with enough velocity to overcome solar radiation pressure and solar wind. And you need the ejection to be sustained over weeks, not just a brief burst. The energy requirements are substantial. On a natural comet, outgassing is driven by solar heating. The sun warms one side of the nucleus, ice sublimates, and gas escapes. But this process is inherently inefficient and undirected. The gas expands in all directions from the heated surface, and the solar wind immediately begins pushing it away from the sun. To get a sunward jet, you would need something actively pushing material in that direction with considerable force. Loeb has pointed out that if 3I Atlas were artificial, a sunward jet would make perfect sense as a thruster firing to make course corrections. Spacecraft use jets all the time to adjust their trajectories. Fire a thruster on one side, and you push the spacecraft in the opposite direction. A sunward jet would accelerate the object away from the sun, which could be useful for maintaining a specific trajectory or compensating for unexpected perturbations. But here is where the conspiracy theories and the hard science collide in uncomfortable ways. In late August, several independent observers reported that the sunward jet seemed to pulse, that its intensity varied in patterns that did not correlate with the expected rotation period of the nucleus. If 3I Atlas was simply a spinning ice ball, the jets should brighten and dim in a regular cycle as active areas rotate in and out of sunlight. Instead, the variations appeared irregular, almost deliberate. No peer-reviewed paper has confirmed the pulsing pattern yet, and Professor Loeb has been careful not to endorse these claims without more data. But the amateur astronomy community, which has been obsessively documenting every image of 3I Atlas, has compiled time-lapse sequences that show the sunward jet changing intensity over timescales of hours. If confirmed, this would add another layer of strangeness to an already inexplicable phenomenon. The European Space Agency's observations from Mars Express in early October, after the sunward jet had mostly dissipated, showed no obvious structural damage to the nucleus that would explain such directed outgassing. The object appeared intact, not fragmenting, not showing the kind of violent activity you might expect from a comet producing anomalous jets. There is also the question of composition. The sunward jet, when analysed spectroscopically, showed similar chemical signatures to the normal tail: carbon dioxide, water, carbon monoxide, and traces of more complex molecules. This suggests the material was coming from the same source, the nucleus itself. But the velocity distributions were different. Material in the sunward jet was moving faster than material in the normal tail, again pointing to some kind of energetic process beyond passive sublimation. By September, the sunward jet had faded, and 3I Atlas developed a more conventional appearance as it approached perihelion. But the damage to the natural comet hypothesis was already done. For 6 to 8 weeks, this object had behaved in a way that comets simply do not behave. It had pushed material toward the sun with enough force and consistency to create a visible feature that multiple observatories documented. Critics of Professor Loeb argue that we are still learning about interstellar comets, and that perhaps they possess characteristics we do not yet understand. This is absolutely true. We have only observed 3 such objects, and each has shown surprising features. But the response to unusual observations should be investigation, not dismissal. The sunward jet demands explanation, and so far no natural mechanism has been proposed that adequately accounts for the data. What makes the sunward jet particularly compelling as an anomaly is that it occurred early in the approach, when 3I Atlas was still relatively far from the sun, and solar heating should have been minimal. If outgassing were the explanation, we would expect the jets to strengthen as the comet got closer and hotter. Instead, the sunward jet was most prominent in July and August, then diminished as the object neared perihelion. This is backwards from what natural processes would predict. There is also timing to consider. The sunward jet appeared just as astronomers around the world were ramping up their observations of 3I Atlas. It was visible long enough to be thoroughly documented, but disappeared before the object moved behind the sun from Earth's perspective. If you were trying to demonstrate capability, to show that you are not just a passive rock tumbling through space. This would be an effective way to do it. Fire your thrusters when people are watching, then go quiet. Professor Loeb has been accused of seeing aliens everywhere, of letting his hypothesis drive his observations rather than the other way around. But when you read his papers, what you find is a scientist presenting data and asking questions. He does not claim the sunward jet proves 3i Atlas is artificial. He claims the sunward jet is anomalous and demands further study. There is a profound difference between these positions. In his November 6th blog post, Loeb noted that the sunward jet, combined with the ecliptic alignment, creates a pattern that is difficult to ignore. One anomaly might be chance. Two anomalies start to look like something systematic, and we are not even close to finished with the list. The physics community has largely remained silent on the sunward jet. This is not because they are covering anything up, but because the observations are so far outside normal experience that most researchers simply do not know what to make of them. It is easier to wait for more data than to speculate about mechanisms that might not exist. But the data is not going to change. Multiple telescopes, multiple observers, multiple independent analyses all confirm the same thing. During July and August 2025, 3i Atlas produced a jet of material that pointed toward the Sun and persisted for weeks. This happened. It is documented. It is real. As 3i Atlas continues its journey through our solar system, astronomers will be watching for any signs that the sunward jet returns. If the object begins to exhibit similar behaviour as it moves away from the Sun, that would be strong evidence for active manoeuvring. Natural comets do not turn their jets on and off based on observational convenience. What we witnessed in those summer months was either a completely new type of cometary activity that somehow went unnoticed in centuries of astronomical observation, or it was something else. Something that operates by different rules. Something that uses jets not for random outgassing, but for control. The mass paradox 1,000,000 times Oumuamua. When scientists first began calculating the size and mass of 3i Atlas, they expected it to be comparable to 2i Borisov, the previous interstellar comet discovered in 2019. Borisov had a nucleus roughly 0.5 kilometre across, small by solar system standards, but reasonable for an object ejected from another planetary system. What they found with 3i Atlas shattered those expectations. The nucleus of 3i Atlas is enormous. Using multiple observation techniques including brightness measurements, thermal emissions, and the extent of its coma, astronomers converged on an estimate that made them check their calculations repeatedly. The solid nucleus is approximately 5 to 10 kilometres in diameter. To put this in perspective, that is larger than most asteroids in our own asteroid belt. It is comparable in size to some of the moons of Mars. Professor Loeb calculated the minimum mass based on these size estimates, and the objects observed non-gravitational acceleration, which we will explore in detail in a later chapter. Assuming a relatively low density typical of comets, around 0.5 gram per cubic centimetre, 3i Atlas must weigh at least 33 billion tonnes. That is 33 followed by 9 zeros, 33,000 million tonnes. This mass is approximately 1 million times greater than 1i Oumuamua and roughly 1,000 times greater than 2i Borisov. Let that sink in for a moment. We have detected 3 interstellar objects. The first was tiny, perhaps 100 metres across. The second was small, maybe 0.5 kilometre. The third is gigantic, 5 to 10 kilometres in diameter. The progression does not make statistical sense. If interstellar objects are randomly ejected from planetary systems across the galaxy, we should see a distribution heavily weighted towards smaller objects. This is basic physics. It takes less energy to eject a small object than a large one. Gravitational slingshots, stellar encounters, planetary perturbations, all of these mechanisms favour the ejection of smaller bodies. Large objects are harder to accelerate to escape velocity. In our own solar system, the size distribution of objects follows a power law. For every large asteroid, There are hundreds of medium-sized ones and millions of small ones. The same pattern should hold for interstellar space. Small objects should vastly outnumber large ones. So why, in our tiny sample of 3 detected interstellar visitors, do we have one giant? The statistical improbability compounds when you consider detection bias. Our telescopes are much better at spotting large bright objects than small dim ones. One Oumuamua was only detected because it passed extremely close to Earth and reflected sunlight efficiently despite its small size. We got lucky. For every Oumuamua-sized object that enters our solar system, dozens probably go unnoticed, because they are too small and too far away to reflect enough light. If small interstellar objects are both more common and harder to detect, we should have seen dozens or hundreds of them before finally spotting one as large as 3I Atlas. The fact that we detected a giant object on only our 3rd confirmed interstellar visitor suggests something is fundamentally wrong with our assumptions. Professor Loeb has pointed out that the mass of 3I Atlas, combined with its velocity, represents a staggering amount of kinetic energy. This object is moving at approximately 210,000 kilometers per hour relative to the Sun. That velocity combined with 33 billion tons of mass means 3I Atlas is carrying energy equivalent to thousands of nuclear weapons. If it were on a collision course with Earth, which it is not, the impact would be extinction level. But the mass paradox is not just about size. It is about what that size implies for the object's origin and journey. For a natural comet to reach 5 to 10 kilometers in diameter, it must have formed in a relatively undisturbed environment where small particles could gradually accrete over millions of years. This happens in the outer regions of planetary systems, in zones analogous to our Kuiper belt or Oort cloud. Once formed, this massive object would need to be ejected from its home system. But ejecting something this large requires a significant gravitational kick. A close encounter with a gas giant planet might do it, or a stellar flyby that perturbed the entire outer system. These events are possible but not common. And then, after ejection, the object must survive millions or billions of years of interstellar travel without fragmenting, without colliding with anything substantial, without being gravitationally captured by another star. The odds of all these events occurring, and then having the object arrive in our solar system precisely when we have the technology to detect it, are vanishingly small. This is what astronomers call a selection effect problem. We might be seeing something rare not because it is rare, but because we are in the wrong position to understand what is common. However, there is another explanation that cannot be easily dismissed. If 3I Atlas is not a natural comet but a technological construct, the mass paradox disappears. Large spacecraft make sense. If you are going to travel between stars, you want to carry equipment, fuel, supplies, shielding. You want redundancy. You want mass to absorb micrometeorite impacts during the multi-million-year journey through interstellar space. A city-sized spacecraft would not be unprecedented in science fiction, and increasingly not in serious scientific speculation either. The energy requirements to accelerate such a massive object to interstellar velocities are enormous, but a sufficiently advanced civilization with access to stellar-scale energy could manage it. And if you are planning a multi-million-year mission, you build big because you cannot count on resupply. The images captured by Hubble Space Telescope in July 2025 showed 3I Atlas as a fuzzy blob with a developing coma, exactly what you would expect from either a comet or a spacecraft deliberately venting material. The nucleus itself was not resolved, meaning we cannot see surface details, cannot determine if there are structures or if it is just an irregular chunk of ice and rock. At a distance of hundreds of millions of kilometers, even Hubble's powerful optics cannot provide that level of detail. What the mass does tell us is that 3I Atlas is not fragile. Smaller comets often fragment when they approach the Sun, torn apart by thermal stress and tidal forces. 2I Borisov showed some signs of fragmentation during its perihelion passage. But 3I Atlas, despite passing much closer to the Sun than Borisov did, appears to have remained intact. Its sheer mass may have provided structural integrity that smaller objects lack. The mass also explains why 3I Atlas has been so bright and so easily observable. A large nucleus has a large surface area, which means more ice can sublimate, creating a bigger coma and more reflected sunlight. This is one reason we detected 3I Atlas months before perihelion, giving astronomers an unprecedented opportunity to study an interstellar object over an extended period. But here is where the mass paradox intersects with the other anomalies in troubling ways. An object this massive, travelling this fast, exhibiting non-gravitational acceleration, requires a tremendous amount of outgassing to alter its trajectory. We are talking about billions of tons of material being ejected into space. If 3I Atlas is a natural comet and its course changes are due to cometary jets, there should be an enormous debris cloud surrounding it, visible to every telescope pointed in its direction. As of November 11th, 2025, that debris cloud has not been observed. The object has a coma, certainly, but not the massive plume of gas and dust that should accompany the kind of mass loss required to explain its trajectory changes. This absence is so glaring that Professor Loeb has designated it as the 10th anomaly, which we will examine in detail later. The mass of 3I Atlas also raises questions about its discovery. Why now? Why did we not detect an object this large and this bright decades ago as it approached from interstellar space? The answer is partly technological. Our sky survey capabilities have improved dramatically in recent years. The Atlas system that discovered 3I Atlas was specifically designed to detect near-Earth objects and has remarkable sensitivity. But there is also the trajectory to consider. 3I Atlas approached from the direction of the constellation Sculptor, a relatively sparse region of sky that is not monitored as intensely as areas closer to the ecliptic plane. It is possible, even likely, that the object was visible to powerful telescopes for years before anyone noticed it. We only pay attention to what moves, and 3I Atlas did not move noticeably against the background stars until it was relatively close. The comparison to 1I Oumuamua is instructive. Oumuamua was tiny, and was only detected after it had already passed perihelion, and was leaving the solar system. We caught it on its way out, almost by accident. With 3I Atlas, we have months of advance warning, months of observations, months to study it before, during, and after perihelion. The difference is the mass. Size matters. Professor Loeb has emphasized that the mass paradox, standing alone, is not proof of anything. Large interstellar objects must exist, and eventually we were bound to detect one. But the mass becomes increasingly difficult to explain naturally when combined with the trajectory, the jets, the composition anomalies, and all the other strange features we are documenting. The question we should be asking is not whether 3I Atlas could be natural despite its size, but whether we would expect a technological probe to be this large. And the answer, surprisingly, is yes. If you are crossing the galaxy, you do not send a CubeSat. You send something substantial, something that can survive the journey, something that can carry out its mission when it arrives. 3I Atlas is substantial. It is surviving. And if the other anomalies are any indication, it is carrying out some kind of mission right now, in real time, as it moves through our solar system under the watchful eyes of every telescope that can track it. Perfect timing, the fine-tuned arrival. There are moments in science when the mathematics become so uncomfortable that you have to step back and question everything. The timing of 3I Atlas arrival at our solar system is one of those moments. Professor Loeb calculated the probability that an interstellar object would arrive with a trajectory that brings it close to multiple planets, while remaining largely unobservable from Earth during its most active period. The number he arrived at is 0.005%. That is 5/1000ths of 1%, 1 in 20,000. Let us break down what this means. 3I Atlas reached perihelion on October 29th, 2025, passing just over 200 million kilometres from the Sun. On that exact date, the object was in solar conjunction from Earth's perspective, meaning it was positioned almost directly on the opposite side of the Sun from us. During the weeks before and after perihelion, when a comet should be at its brightest and most active, 3I Atlas was hidden in the Sun's glare, unobservable by ground-based telescopes. This was not a brief occultation. For more than 35 days from late September through early November, 3I Atlas was effectively invisible from Earth. We could not see it. We could not study it. We could only watch it with a handful of spacecraft that happened to be positioned elsewhere in the solar system. The timing of this solar conjunction was exquisitely precise. If 3I Atlas had arrived a few weeks earlier or later, it would have been visible from Earth during perihelion. Astronomers could have trained dozens of major observatories on the object during its closest approach to the Sun, capturing detailed spectra, monitoring its outgassing in real time, observing any changes to its nucleus. Instead, we got silence. We got a blackout period precisely when we should have had maximum visibility. Coincidence? Perhaps. But the probabilities say otherwise. The orbital mechanics of interstellar objects are complex, influenced by the gravitational fields of every star system they pass near during their multi-million-year journeys. For an object to arrive at our solar system and naturally time its perihelion passage to coincide with solar conjunction from Earth requires an extraordinary alignment of circumstances. Think of it this way. Earth orbits the Sun once per year. At any given moment there is a narrow band of sky, perhaps 20 to 30 degrees wide, where the Sun appears from Earth's perspective. Objects in that band are invisible to us because they are drowned out by solar glare. For 3I Atlas to pass through perihelion while positioned in that narrow band, arriving from interstellar space on a hyperbolic orbit that took millions of years to complete, is the astronomical equivalent of threading a needle in the dark. But the timing anomaly goes deeper. 3I Atlas did not just hide from Earth during perihelion. It also arranged close encounters with Mars, Venus and Jupiter at specific moments when those planets were optimally positioned for observation. On October 3rd, it passed Mars when the red planet was well placed for imaging by multiple orbiters. It approached Venus in early November when the geometry was favourable for spacecraft observations, and it will arrive at Jupiter in March 2026, when Juno is in position to potentially capture data. If you were planning a grand tour of the inner solar system, if you wanted to study multiple planets while minimising observation from the dominant technological species on the third planet, this is exactly the trajectory you would choose. You would time your arrival so that Earth-based telescopes are blinded during your most vulnerable moment, your closest approach to the Sun. You would arrange flybys of other worlds when your own spacecraft and probes could observe them. You would optimise for your mission, not for the convenience of human astronomers. Professor Loeb has pointed out that the arrival time also coincides with a period of unprecedented observational capability in human history. We have multiple Mars orbiters, Venus orbiters until recently, Jupiter orbiters, solar observatories, and interplanetary spacecraft scattered throughout the inner solar system. 20 years ago, we would have had far fewer eyes on 3I Atlas. 20 years from now, we will have even more. The object arrived during a narrow window when we were advanced enough to detect it, but limited enough that we cannot study it as thoroughly as we might wish. Some critics argue that this is selection bias, that we are reading intent into randomness because humans are pattern-seeking creatures. But selection bias works both ways. If interstellar objects are common and arrive constantly, we should have detected dozens by now with our improving sky surveys. The fact that we have only confirmed 3 suggests these visits are rare, and if they are rare, the timing of each visit becomes more, not less, significant. The October 29th perihelion date also placed 3I Atlas in a specific region of its orbit where spacecraft like Europa Clipper and potentially Hera could pass through its ion tail. This was not guaranteed. The spacecraft trajectories were planned years in advance, long before 3I Atlas was discovered. Yet the geometry worked out such that these missions, heading to completely different destinations, found themselves in position to sample material from an interstellar visitor. Coincidence or coordination? The ESA's JUICE mission was also positioned to observe 3I Atlas during November, though from the opposite side of the Sun from Earth. The fact that so many spacecraft happened to be in useful positions at exactly the right time strains credibility. Either we are experiencing extraordinary luck, or something about 3I Atlas' trajectory was designed to take advantage of existing human space infrastructure. There is also the question of advance warning. 3I Atlas was discovered in July, giving astronomers 4 months to prepare for perihelion. This is longer than we had for either Oumuamua or Borisov. The timing allowed the scientific community to mobilise, to plan observation campaigns, to coordinate between observatories and space agencies. If the object wanted to announce its presence without causing panic, a gradual approach with months of advance visibility is exactly how you would do it. The government shutdown in the United States, which began on October 1st and coincided almost perfectly with the final approach of 3I Atlas, added another layer of complexity. NASA's data release slowed to a crawl. The high-rise images from Mars Reconnaissance Orbiter, which captured 3I Atlas at unprecedented resolution on October 2nd, were not released for over a month. The European Space Agency published their Mars Express and ExoMars observations quickly, but American data remained locked behind bureaucratic walls. Was the timing of the shutdown coincidental? Almost certainly. Government funding lapses happen for political reasons that have nothing to do with interstellar visitors. But the effect was real. During the most critical observation period, when 3I Atlas was approaching, and then, passing perihelion, the flow of information from NASA slowed dramatically. Conspiracy theorists seized on this, claiming a cover-up. More likely, it was simply bad timing compounded by administrative dysfunction. The Akatsuki announcement on October 28th adds fuel to these fires. Japan's Venus orbiter had been silent since April 2024, yet JAXA waited 17 months to officially declare it dead, making the announcement one day before 3I Atlas reached perihelion. The timing seems almost deliberately provocative, as if designed to raise questions. Why announce now? Why not wait until after the perihelion passage? Unless, of course, the announcement was timed to provide an excuse for why Venus observations during the approach would be limited. Professor Loeb has been careful to distinguish between what we know and what we suspect. The timing of 3I Atlas arrival is documented fact. The 0.005% probability is calculated from orbital mechanics and observational geometry. These are not speculations. What remains speculative is whether the timing is intentional or merely the universe's most elaborate joke. If 3I Atlas is a natural comet, then its timing is just luck, extraordinary luck, but luck nonetheless. The laws of physics do not care about human observation capabilities, or political shutdowns, or spacecraft positions. Natural objects arrive when they arrive, and we deal with the consequences. But if 3I Atlas is something else, if it is guided, if it is intentional, then the timing makes perfect sense. You would want to minimize observation during your most vulnerable moment. You would want to study other worlds when you have the best vantage point. You would want to arrive when the target species had just enough technology to notice you, but not enough to threaten you. The fine-tuning extends to the orbital parameters themselves. 3I Atlas has an eccentricity of approximately 1.04, just barely hyperbolic, just barely interstellar. If the eccentricity was slightly lower, the object might have been bound to the Sun, making it a solar system comet that somehow went undetected for billions of years. If the eccentricity were higher, it would be moving faster, giving us less time to observe it. The value is right at the boundary, maximising our observation window while maintaining clear interstellar credentials. December 19th, 2025 looms on the calendar. That is when 3I Atlas makes its closest approach to Earth. passing within 167 million miles of our planet. By then, the object will be visible again to ground-based telescopes, emerging from behind the sun like a performer taking the stage after a costume change. What we see in those coming weeks may determine whether the timing anomaly remains a mathematical curiosity or becomes evidence of something far more profound. For now, we are left with probabilities. 1 in 20,000 chance of the timing being random, 1 in 500 chance of the trajectory being random. These numbers do not prove anything, but they demand explanation. They force us to ask whether we are witnesses to the universe's most improbable sequence of coincidences, or whether we are watching something unfold according to a plan we are only beginning to comprehend. Industrial nickel without iron, the alloy mystery. In late August 2025, an international team of astronomers published findings that sent shockwaves through the planetary science community. They had detected nickel vapour in the coma of 3I Atlas, at a distance of approximately 3.9 astronomical units from the Sun, far beyond where nickel should be vaporizing. But the real anomaly was not the presence of nickel, it was the absence of iron. Comets are dirty snowballs, mixtures of ice and rock that formed in the outer regions of planetary systems billions of years ago. When we analyse the composition of solar system comets, we find metals trapped in silicate grains, tiny particles of rock embedded in the ice. As the comet heats up near the Sun, these silicates begin to vaporise, releasing metal atoms into the coma. Nickel and iron are common constituents of these grains, and they always appear together because they form together in stellar nucleosynthesis and are chemically bonded in the same mineral structures. The ratio of nickel to iron in natural materials is well established. In asteroids, comets, meteorites and planetary crusts, iron is always far more abundant than nickel, typically by a factor of 10 to 20. This is not arbitrary. It reflects the fundamental abundance of these elements in the universe, and how they condensed during the formation of the solar system. 3I Atlas violates this pattern spectacularly. The spectroscopic observations showed strong nickel emission lines, but no detectable iron above instrumental noise levels. The nickel to iron ratio was not just unusual, it was inverted, impossible, completely inconsistent with natural processes. Professor Loeb immediately recognised the significance. In human metallurgy, we produce nickel alloys by deliberately separating nickel from iron and combining it with other elements to create materials with specific properties. Stainless steel, superalloys for jet engines, corrosion-resistant marine equipment, all of these rely on purified nickel in concentrations far higher than natural ores provide. The industrial separation of nickel and iron is a hallmark of technological civilization. The paper documenting the nickel anomaly tried to offer natural explanations. Perhaps nickel and iron are released from different types of grains that vaporize at different temperatures. Perhaps the observational geometry somehow made iron harder to detect. Perhaps 3I Atlas formed in a region of its parent system with unusual chemistry. Each explanation was carefully worded, scientifically cautious, and fundamentally unsatisfying. The temperature argument does not hold up under scrutiny. At 3.9 astronomical units, 3I Atlas was still quite cold, far too cold for silicate vaporization driven purely by solar heating. For nickel to appear in the coma at that distance requires some mechanism beyond passive warming, and if that mechanism preferentially releases nickel without iron, you need to explain why nature would create such a selective process. The observational geometry argument is even weaker. Iron has strong spectral lines that should be easily detectable if the element is present in anything close to normal abundances. The fact that multiple independent observations with different instruments all failed to find iron suggests it genuinely is not there, not that we are looking in the wrong way. The unusual formation chemistry argument is perhaps the most interesting, because it implicitly acknowledges that 3I Atlas composition is unlike anything we've seen before. If the object formed in a planetary system with different elemental abundances than our own, that tells us something profound about the diversity of chemical environments across the galaxy. But it does not explain why such a system would produce high nickel and low iron. Stellar nucleosynthesis does not work that way. Iron is always created in greater abundance than nickel in supernova explosions and stellar cores. What remains is the possibility that the nickel emission is not coming from natural vaporization of silicate grains, but from something else. If 3I Atlas is venting material that has been processed, refined, or synthesized, the spectral signature could look exactly like what we are observing. Industrial alloys would give you high nickel without iron. Heat-shielding materials would give you unusual metal ratios. Propellant residues could contain metals in non-natural configurations. The detection itself was remarkable for another reason. Nickel vapor is difficult to observe because it requires specific wavelengths and sufficient concentration to produce detectable emission lines. The fact that it showed up so clearly, so early in the approach, suggests large quantities of nickel-bearing material were being released into space. This is consistent with active outgassing, but natural comets do not preferentially vent one metal while excluding another. Additional observations in September and October tracked the evolution of the nickel emission as 3I Atlas approached the Sun. Instead of increasing steadily with solar heating as expected, the nickel signature varied in intensity, sometimes spiking dramatically before fading again. This irregular pattern is difficult to reconcile with passive sublimation, which should follow the smooth curve of increasing solar flux. There is also the ratio of nickel to cyanide, another molecule detected in the coma. 3I Atlas showed a nickel to cyanide ratio orders of magnitude higher than any known comet. Cyanide is common in comets, formed from carbon and nitrogen in the cold outer regions of planetary systems. Nickel, while present, is typically much less abundant. For 3I Atlas to flip this ratio suggests either a completely alien formation environment or active processing of materials. Professor Loeb has drawn parallels to human spacecraft, which often use nickel-based alloys in critical components exposed to extreme temperatures or corrosive environments. The Voyager probes, Pioneer spacecraft, even the heat shields on Mars landers employ high nickel materials because of their thermal stability and resistance to degradation. If 3I Atlas were artificial, the detection of industrial-scale nickel without accompanying iron would be expected, not anomalous. Critics point out that we have limited data on interstellar comet compositions. 2I Borisov, our only other well-studied interstellar comet, showed chemical signatures broadly consistent with solar system comets, but with some differences. Perhaps 3I Atlas is simply another data point in a distribution we do not yet understand. This argument has merit, but it sidesteps the fundamental question: why would natural processes produce such an extreme nickel to iron ratio? The timing of the nickel detection is also worth noting. It occurred in late August, just as the sunward jet was becoming most prominent, and just before 3I Atlas disappeared behind the sun from Earth's perspective. If you were trying to demonstrate that your composition is not natural, releasing large quantities of high-purity nickel into space would send a clear signal to anyone with a spectrograph. There is a darker interpretation that some researchers whisper about but rarely publish. What if the nickel is not structural material but propellant residue? Certain theoretical propulsion systems, including some fusion concepts and advanced ion drives, could produce exhaust containing heavy metals. If 3I Atlas is maneuvering using technology beyond our current understanding, the nickel emission might be the signature of its engines. This speculation goes far beyond what the data supports, but it illustrates how the anomaly forces us into uncomfortable territory. Every conventional explanation for the nickel-to-iron ratio requires special pleading, requires assuming 3I Atlas is unlike any object we have ever studied. At some point, Occam's razor starts cutting in the other direction. Perhaps the simplest explanation is the one we are most reluctant to consider. The chemical analysis also revealed unusually high, carbon dioxide concentrations and surprisingly low water content, which we will examine in the next chapter. But the metals stand out because they are difficult to misinterpret. Spectral lines are precise. You cannot mistake nickel for something else. When you see strong nickel emission and no iron, you cannot explain it away with observational uncertainties. The scientific papers discussing 3I Atlas composition are careful to avoid sensational language. They present data, note anomalies, suggest areas for further research. But between the lines, you can sense the unease. This object is not behaving like comets behave. Its chemistry is wrong. Its metal ratios are impossible. Professor Loeb has called the nickel anomaly one of the most compelling pieces of evidence that 3I Atlas might not be entirely natural. Combined with the trajectory, the timing, the jets and the mass, it creates a composite picture that becomes harder to wave away with each additional observation. One anomaly is interesting. 5 anomalies is a pattern. As 3I Atlas moves away from the inner solar system, spectroscopic observations will continue tracking the evolution of its coma composition. If the nickel emission persists or changes in ways inconsistent with cometary outgassing models, the anomaly will strengthen. If iron suddenly appears in the expected ratios, we will need to explain why it was absent earlier. Either outcome is significant. For now, we are left with metal vapour in space, distributed in ratios that make metallurgists uncomfortable and planetary scientists confused. The nickel is real. The absence of iron is real. The implications are unavoidable. Whatever 3I Atlas is made of, it is not made of the same stuff as other comets, and that difference might tell us everything we need to know about where it came from and why it is here. Extreme negative polarization, dust from another world. Light has a hidden property that most people never think about. When sunlight bounces off an object, it becomes polarized, meaning the light waves align in specific directions. This polarization carries information about the surface and composition of whatever reflected it. For astronomers, measuring polarization is like taking a fingerprint of distant objects, revealing details invisible to ordinary imaging. In September 2025, a team led by researchers using the Very Large Telescope in Chile published polarimetric observations of 3I Atlas that defied everything we know about comets, asteroids, and small solar system bodies. The object showed extreme negative polarization of minus 2.77% at a phase angle of about 7 degrees, with an inversion angle of only 17 degrees. To understand why this matters, we need to understand what those numbers mean. When light scatters off dust particles, the polarization can be positive or negative depending on the viewing angle and the properties of the dust. Most comets show negative polarization at small phase angles, typically around minus 1 to minus 1.5%. This is normal, this is expected. 3I Atlas showed nearly double that value, pushing into territory never observed before. The inversion angle, the point where polarization switches from negative to positive, is equally troubling. Solar system comets typically show inversion angles between 20 and 30 degrees. 3I Atlas inverted at 17 degrees, significantly lower than any known comet. The combination of extremely deep negative polarization and low inversion angle places the object in a category of its own, completely isolated from the distribution of every other body we have measured. Polarization is determined by the size, shape, composition, and surface texture of dust grains. When scientists model the polarization signature of 3I Atlas, they cannot find any combination of normal cometary dust properties that reproduces the observations. The dust would need to be fundamentally different from anything we have encountered, with optical properties unlike any natural material in our solar system. The closest analogues in the astronomical zoo are certain trans-Neptunian objects like Huya, Ixion and Varuna, small icy worlds in the outer solar system that show unusually steep polarization curves. But even these objects do not match 3I Atlas exactly. The comet occupies its own unique position in polarization space, an outlier among outliers. Professor Loeb has noted that the extreme polarization could indicate dust grains with layered structures, unusual chemical compositions, or manufacturing processes that do not occur in nature. If you were to design dust particles for a specific purpose, say for radiation shielding or thermal control, you might end up with grains that scatter light in unusual ways. The polarization signature would be a byproduct of engineering, not evolution. The observations were made using the Forest 2 instrument on the Very Large Telescope, one of the most sophisticated polarimeters available to astronomers. Multiple observations at different epochs confirmed the anomaly. This was not a measurement error or a fleeting phenomenon. The extreme polarization was persistent, reproducible, and completely unprecedented. What makes this particularly interesting is that polarization is sensitive to grain sizes on the scale of the wavelength of light, around half a micrometer. This is much smaller than what we can resolve with imaging. Polarimetry lets us probe the microscopic structure of the dust surrounding 3I Atlas, and what we are seeing does not match natural cometary dust. The research paper describing the polarization anomaly tried to fit the observations using standard dust models, varying parameters like grain size distribution, composition, porosity, and shape. Nothing worked. Every model that matched the depth of the negative polarization failed to reproduce the low inversion angle. Every model that got the inversion angle right could not achieve the extreme negative values. The dust defies modelling. One possibility is that 3I Atlas formed in a region of its parent planetary system, exposed to higher levels of radiation than is typical in our solar system. Cosmic ray bombardment can alter the surface properties of dust grains, potentially creating unusual optical characteristics. But this explanation requires the object to have formed in an environment fundamentally different from where solar system comets originated, which brings us back to the question of how common such environments are, and why we happen to detect an object from one so early in our survey of interstellar visitors. Another explanation involves the composition itself. If the dust contains minerals or ices not found in solar system comets, the polarization signature could naturally differ. We know from spectroscopy that 3I Atlas has unusual chemistry, high carbon dioxide, low water, strange metal ratios. Perhaps the dust composition is equally alien, containing materials that formed under conditions we have never studied. But there is a third possibility that cannot be ignored. Manufactured materials, especially composites and alloys, can have optical properties quite different from natural minerals. Spacecraft are covered in materials designed to reflect, absorb, or scatter light in specific ways. Heat shields, solar panels, antenna surfaces, structural components, all of these have been engineered to interact with electromagnetic radiation in controlled manners. If 3I Atlas were shedding material from a technological surface, the polarization signature might look exactly like what we are observing. The extreme polarization was detected early in 3I Atlas approach, when the object was still relatively far from the Sun, and outgassing should have been minimal. This suggests the dust was already present in the coma, not freshly released by solar heating. Where did it come from? Natural comets develop comas gradually as they warm up. 3I Atlas seemed to arrive with a pre-existing cloud of dust that had optical properties unlike any cometary dust we have measured. As the object approached perihelion and outgassing increased, additional polarimetric observations tracked how the signature evolved. Surprisingly, the extreme negative polarization persisted even as more material was released. If the anomaly were due to a small population of unusual grains being diluted by normal cometary dust, we would expect the polarization to become less extreme over time. Instead, it remained consistently anomalous. The researchers who published the polarization findings have been careful to present it as an observational result requiring further study. They do not claim it proves 3I Atlas is artificial, but they also cannot explain it with natural processes. The paper concludes by noting that the object represents a previously unobserved population, which is a polite way of saying it does not fit anywhere in our existing taxonomies. Professor Loeb has integrated the polarization anomaly into his broader argument about 3-eye atlas. Taken alone, strange dust properties might be explained by unusual formation, conditions, but combined with the trajectory, timing, mass, jets, and chemical composition, the polarization becomes another piece of evidence that this object is fundamentally different from what we have encountered before. There is also a historical parallel worth considering. When the first images of one-eye Oumuamua were analysed, some researchers noted its unusual shape, highly elongated, tumbling rapidly. The shape was explained as natural, the result of tidal forces or collisional history. But the shape also happens to be optimal for a light sail, a thin, reflective surface pushed by solar radiation. The ambiguity was never resolved because Oumuamua left the solar system before we could study it in detail. With 3-eye atlas, we have the opposite situation. Instead of shape being the anomaly, it is dust properties. Instead of speculation about light sails, we are seeing polarization signatures that suggest engineered materials. The specific anomaly has changed, but the underlying question remains the same. Are we looking at nature doing something we do not understand, or are we looking at technology? The polarization measurements will continue as 3-eye atlas moves away from the Sun and becomes visible again from Earth. If the signature changes in predictable ways as the object cools and outgassing diminishes, that would support a natural explanation. If the extreme polarization persists or evolves in unexpected ways, the mystery deepens. What we know for certain is that the dust surrounding 3-eye atlas is not like other dust. Its optical properties place it outside the known distribution of cometary, asteroidal and planetary materials. Whether this reflects an exotic natural composition or something else is a question that polarimetry alone cannot answer. But it is a question we cannot ignore. Light bouncing off 3-eye atlas is trying to tell us something. The polarization is a message encoded in the orientation of electromagnetic waves, a signal that this object is not what we expect. Whether we're capable of interpreting that message correctly remains to be seen, but we cannot claim we were not warned. The light itself is telling us this dust is different, this object is different, and we need to pay very close attention to what comes next. The water enigma, 4% and carbon dioxide dominance comets are supposed to be icy. This is fundamental to our understanding of what comets are and how they formed. When we think of a comet nucleus, we imagine a mixture of water, ice and rock, with water typically comprising 50 to 80% of the total mass. Water is abundant in the universe. It forms easily in cold environments. Every comet we have studied in detail, from Halley to Churyumov-Gerasimenko to 2-eye Borisov, has been dominated by water ice. 3-eye Atlas is not. In August 2025, observations from the Spheric Space Telescope revealed that the coma surrounding 3-eye Atlas contained only about 4% water by mass. 4%. For a comet, this is incomprehensibly low. Instead of water, the coma was dominated by carbon dioxide, CO2, at concentrations far exceeding anything observed in solar system comets. The implications of this finding are staggering. Water and carbon dioxide have different volatility, meaning they vaporize at different temperatures. Water ice sublimates significantly at temperatures above about 170 Kelvin, which occurs at roughly 3 astronomical units from the Sun in our solar system. Carbon dioxide is more volatile, sublimating at lower temperatures, starting around 50 Kelvin. For 3-eye Atlas to show carbon dioxide dominance and water depletion suggests it formed in an environment much colder than where solar system comets originated, or it has been processed in ways that preferentially removed water. Neither explanation is straightforward. If the object formed in the outer regions of another planetary system, beyond where water ice is stable, you might expect high carbon dioxide, but you would still expect some water. 4% is not just low, It is almost trace level, suggesting water was actively excluded or removed rather than simply being less abundant. The Spherix observations were confirmed by the James Webb Space Telescope, which observed 3I Atlas on August 6, 2025, using its near-infrared spectrograph. JWST detected strong carbon dioxide absorption features, along with carbon monoxide, water ice, and carbonyl sulfide. But again, the ratios were all wrong. Carbon dioxide dominated the spectrum with water as a minor constituent. Professor Loeb has pointed out that carbon dioxide propellant systems are commonly used in spacecraft attitude control. Small thrusters that pulse CO2 gas can adjust orientation and trajectory without the complexity of liquid fuel systems. If 3I Atlas were artificial, the abundance of carbon dioxide and scarcity of water might reflect its propulsion and control systems rather than its bulk composition. But there is another possibility that planetary scientists find even more intriguing and unsettling. What if 3I Atlas did form as a normal water-rich comet, but during its multi-million-year journey through interstellar space, it underwent selective loss of water while retaining carbon dioxide? This could happen through cosmic ray bombardment, which can break chemical bonds and allow lighter molecules like water to escape more easily than heavier molecules like CO2. The problem with this explanation is that we have no observational evidence for such a process. 2I Borisov did not show preferential water depletion. 1I Oumuamua showed no signs of outgassing at all. If interstellar travel naturally removes water from comets, we should see this pattern consistently. We do not. There is also the thermodynamic question. Carbon dioxide sublimation releases less energy per molecule than water sublimation. For an object dominated by CO2 to produce the observed coma and activity level, it would need to be venting enormous quantities of material. This is consistent with the object's brightness and the extent of its coma, but it also means 3I Atlas is losing mass at a prodigious rate if it is purely natural outgassing. The chemical analysis revealed other oddities beyond just the water to CO2 ratio. The presence of carbonyl sulfide, a molecule rarely detected in comets, suggests 3I Atlas contains sulfur compounds in unusual forms. The carbon monoxide abundance was also elevated compared to solar system norms. Every chemical signature points to an object that formed under conditions profoundly different from our cosmic neighbourhood. One research team proposed that 3I Atlas might have formed near the carbon dioxide ice line in its parent protoplanetary disk, the boundary beyond which CO2 can condense, but water remains mostly in vapour form. This would naturally produce a carbon dioxide-rich, water-poor body. But this formation scenario requires very specific temperature and pressure conditions that are not common in planetary system formation models. The low water content also has implications for the object's thermal evolution. Water ice acts as a temperature buffer during solar heating because sublimation absorbs energy. An object with little water will heat up more rapidly as it approaches the sun, potentially leading to more vigorous outgassing of whatever volatile materials are present. This could explain the rapid brightening observed near perihelion, which we will examine in the next chapter. But it also raises questions about structural integrity. Water ice provides cohesion in cometary nuclei, acting as a kind of glue that holds dust and rock together. A comet with only 4% water should be fragile, prone to fragmentation under thermal stress. Yet 3I Atlas appears to have survived perihelion intact, despite coming closer to the Sun than 2I Borisov did. The durability suggests either an unusual internal structure or a composition dominated by more refractory materials, substances that do not easily vaporize. If the bulk of 3I Atlas is made of rock, metal or carbon compounds rather than ice, the low water content makes sense. But then you are no longer describing a comet in the traditional sense. You're describing something more like an asteroid with a thin coating of volatile ices. Professor Loeb has noted that spacecraft and space stations use carbon dioxide extensively in life support systems and as a coolant. the space shuttle used CO2 scrubbers to remove exhaled carbon dioxide from the cabin atmosphere, then vented it into space. A large spacecraft on a multi-million-year journey might vent substantial amounts of CO2 as part of thermal management or atmospheric recycling. This speculation goes beyond what the data strictly supports, but it highlights how the chemical composition anomalies force us into increasingly exotic explanations. If 3I Atlas is natural, it formed in an environment we have never studied and underwent processes during interstellar transit that we do not understand. If it is artificial, the chemical signature is exactly what you might expect from a technological object. The detection of water ice on the surface of 3I Atlas by various telescopes confirms that water is present, just not dominant. Infrared observations show spectral features consistent with small amounts of water ice mixed with or coating other materials. This trace water could be frost accumulated during the long interstellar journey, or it could be residual from the object's formation. What makes the water enigma particularly compelling is that it cannot be explained away as an instrumental artifact or observational bias. Multiple independent instruments using different techniques all converged on the same conclusion. 3I Atlas is carbon dioxide rich and water poor. The chemistry is real, measurable, and completely at odds with what we expect from comets. As the object continues its journey through our solar system, continued spectroscopic monitoring will track how the CO2 to water ratio evolves. If the ratio changes significantly, that would tell us something about the vertical structure and composition of the nucleus. If it remains constant, that suggests the unusual chemistry is representative of the entire object, not just a surface layer. There is also the tantalizing possibility that JWST or other infrared telescopes might detect organic molecules in the coma, compounds containing carbon, hydrogen, oxygen, and nitrogen that could indicate either complex chemistry from the object's formation or something more intriguing. The discovery of amino acids or other prebiotic molecules would not prove anything about the object's nature, but it would certainly add another layer of mystery to an already perplexing visitor. For now, we are left with a comet that is not comet-like, an object rich in carbon dioxide and poor in water, venting gases in ratios that do not match any known population of small bodies. The chemistry is trying to tell us something, whether it is telling us about exotic planetary formation conditions in another star system, or about the composition of something deliberately manufactured, is a question that chemistry alone cannot answer. But the message is clear. 3I Atlas is not made of the same stuff as solar system comets. Its ice is the wrong ice, its chemistry is the wrong chemistry, and the wrongness is consistent, persistent, and deeply, profoundly strange. Rapid brightening and the blue anomaly. On October 29th, 2025, as 3I Atlas reached perihelion, solar observatories watching the region near the Sun detected something extraordinary. The comet brightened rapidly, far more than models predicted, increasing in luminosity by approximately a factor of 5 in just days. But the real surprise was not the brightness increase, it was the colour. 3I Atlas turned blue, distinctly, measurably, impossibly blue. Objects near the Sun should not turn blue. This is basic physics. When dust particles scatter sunlight, they redden the light, filtering out blue wavelengths and allowing red wavelengths to pass. This is the same reason sunsets are red and dust clouds look brown. Dust makes things redder, not bluer. Additionally, the surface temperature of 3I Atlas at perihelion, even accounting for solar heating, should have been far cooler than the Sun's photosphere, which sits at approximately 5800 Kelvin. A cooler body emits thermal radiation shifted toward longer, redder wavelengths. The comet should have appeared distinctly redder than the Sun, not bluer. The observations came from Stereo, SOHO and GOES 19, spacecraft equipped with coronagraphs designed to block the overwhelming glare of the Sun and image the faint corona. 3-eye atlas passed through their fields of view during perihelion, and the images were unambiguous. The object was bright, it was blue, and it should not have been either. Professor Loeb immediately recognised this as the 9th anomaly. He published analysis within days, noting that the blue colour could only be explained by intense gas emission, not dust scattering. Specifically, molecules like carbon-2, diatomic carbon, and possibly nitrogen compounds fluoresce when exposed to intense solar radiation, emitting light at blue-green wavelengths. For this emission to be bright enough to make the entire object appear bluer than the sun requires enormous quantities of gas. The rapid brightening itself was documented in a paper by Qicheng Zhang and Carl Battams, analysing the coronagraph data. They noted that 3-eye atlas brightened at a rate far exceeding typical Oort cloud comets at similar distances. The increase was not gradual or predictable. It was explosive, as if some internal process suddenly activated when the object reached a critical temperature or solar flux. Several explanations have been proposed, none entirely satisfying. One possibility is that water ice sublimation, which had been suppressed earlier in the approach due to cooling from carbon dioxide sublimation, suddenly kicked in near perihelion. The delayed onset of water outgassing could cause a rapid surge in activity, but this does not explain why the object remained so bright and so blue for an extended period, rather than quickly returning to normal appearance. Another explanation involves the unusual composition. If 3-eye atlas contains volatile ices that are rare or absent in solar system comets, these materials might sublimate at specific temperatures near perihelion, triggering sudden activity. The carbon dioxide dominance we discussed earlier could play a role, with CO2 outgassing reaching a critical threshold that destabilizes the surface and exposes fresh material. But there is a third explanation that Professor Loeb has carefully articulated without explicitly endorsing. If 3-eye atlas were using solar energy to power some internal process, a kind of solar thermal or photovoltaic system, the activation of this system near perihelion could release energy in the form of heat and light. The blue colour would not be scattered sunlight or thermal emission, but rather emission from a power source hotter than the surrounding environment. This is speculative, admittedly, but it addresses the central paradox. How does an object get bluer than the sun when basic thermodynamics says it should be redder? You need a source of energy that raises the temperature of emitting material above solar temperatures, or you need chemical processes that produce intense blue-green fluorescence far beyond what natural outgassing achieves. The observations from different instruments were consistent. LASCO on SOHO, CCOR1 on GOES 19, and the Secchi instruments on stereo all captured the same phenomenon. Rapid brightening and a blue colour inconsistent with dust-dominated scattering. Multiple independent confirmations eliminate the possibility of instrumental artifacts. The timing of the brightening, precisely at perihelion, suggests it is triggered by proximity to the sun. Whether this trigger is purely thermal, related to solar flux reaching some critical value, or whether it involves other factors remains unknown. But the correlation between solar distance and activity level is undeniable. What makes the blue colour particularly troubling for natural explanations is that it requires specific molecules in the right excitation states. Carbon-2 emission, the most likely source of the blue colour, occurs when diatomic carbon molecules absorb ultraviolet light from the sun and re-emit at visible wavelengths. This is a well-understood process in comets. But the intensity required to make 3-eye atlas appear bluer than the sun implies carbon 2 concentrations orders of magnitude higher than typical comets. Where does this carbon come from? If the nucleus is carbon-rich, with significant amounts of carbon dioxide and carbon-bearing compounds as the spectroscopy suggests, intense solar heating near perihelion could indeed liberate large amounts of carbon. But carbon-2 is highly reactive. It quickly recombines to form other molecules or condenses onto dust grains. Maintaining high concentrations requires continuous production, continuous outgassing, continuous energy input. The rapid brightening also has implications for mass loss. If 3I Atlas brightened by a factor of 5 due to increased outgassing, it must have been ejecting material at 5 times the previous rate. Over days to weeks near perihelion, this represents an enormous quantity of gas and dust. Where is it all going? Where is the debris cloud? This question connects directly to the 10th anomaly, which we will examine in the final chapter. But the absence of an expected massive debris cloud, even as the object demonstrates clear signs of intense activity and mass loss, creates a logical contradiction. The observations do not fit together unless something about our assumptions is wrong. Professor Loeb has suggested that the rapid brightening and blue colour might be signs of a reverse solar Oberth manoeuvre, a theoretical technique where a spacecraft uses close solar passage to perform a high-thrust burn, taking advantage of being deep in the Sun's gravitational well to maximise the effect. If 3I Atlas were manoeuvring near perihelion, the exhaust plume could appear blue if the propulsion system were hot enough. This is, again, highly speculative, but it addresses multiple anomalies simultaneously. A propulsion system explains the non-gravitational acceleration we will discuss next. It explains the rapid brightening as thruster activation. It explains the blue colour as exhaust emissions, and it explains why the phenomenon occurred precisely at perihelion, when such a manoeuvre would be most effective. The scientific community has been divided in its response to the brightening anomaly. Some researchers view it as evidence of unexpected cometary physics, a reminder that we still have much to learn about how icy bodies behave in extreme solar environments. Others see it as yet another data point in a pattern that is becoming increasingly difficult to attribute to natural causes. The coronagraph images themselves are remarkable. They show a compact, intensely bright source surrounded by a diffuse glow, the classic appearance of a comet near the Sun. But the colour is wrong. The brightness increase is too fast. The persistence of the blue emission is unexplained. In the coming months, as 3I Atlas moves away from the Sun and cools down, observers will watch to see if the object returns to its previous appearance or if it maintains unusual characteristics. If the blue colour was purely due to perihelion heating, it should fade as solar flux decreases. If it persists or reappears at unexpected times, that would suggest the source is not entirely dependent on external heating. The rapid brightening has also raised questions about what we might have missed. 3I Atlas was behind the Sun from Earth's perspective during the most critical days of perihelion passage. The coronagraph observations captured the event, but ground-based telescopes with higher resolution and more sophisticated instruments were blinded by solar glare. We saw the object turn bright and blue, but we did not see it with the detail necessary to fully understand what was happening. This observational gap, created by the precise timing of perihelion at solar conjunction, means we have tantalizing hints of extreme behavior, but not complete data. It is like watching a play through a keyhole, seeing critical moments but missing context. What did 3I Atlas do during those hidden days? Did the brightening continue? Did the colour change? Did the jets intensify? We may never know the full answer, but what we do know is troubling enough. An interstellar object already displaying multiple anomalies brightened rapidly near the Sun and turned a colour that physics says it should not be. The light from 3I Atlas at perihelion was wrong, fundamentally, observably, undeniably wrong. And light does not lie. It carries information encoded in wavelengths and intensities, information that reflects the physical processes generating it. The blue light from 3I Atlas is telling us something happened near the Sun that we do not understand. Whether that something is exotic chemistry, novel physics, or technology is a question that spectroscopy, photometry, and careful observation will eventually answer. But we cannot pretend the anomaly does not exist. The data is real. The blue light was real, and it should not have been. Non-gravitational acceleration without explanation. By late October 2025, orbital calculations for 3I Atlas had become precise enough to detect something subtle but significant. The object was not moving exactly where gravity said it should be. It was accelerating in ways that could not be explained by the gravitational fields of the Sun and planets alone. The detection of non-gravitational acceleration in comets is not new. Many solar system comets show slight deviations from purely gravitational trajectories because they are outgassing, ejecting material that acts like a rocket thrust. When ice sublimates and gas escapes from one side of a rotating nucleus, it pushes the comet in the opposite direction. This is called the rocket effect, and it is well understood, well modelled, and thoroughly documented. What makes 3I Atlas different is the magnitude and character of its acceleration combined with the absence of expected consequences. NASA's Jet Propulsion Laboratory published updated orbital elements on October 29th showing a non-gravitational acceleration of approximately 4.9 times 10 to the negative 6th meters per second squared, normalized to a distance of 1 astronomical unit from the Sun. This is a small but measurable value, detected with a confidence level of approximately 3.7 standard deviations. In simpler terms, 3I Atlas was moving faster or in a slightly different direction than pure gravity would predict, and the deviation was statistically significant, unlikely to be explained by measurement uncertainties alone. Professor Loeb immediately began calculating what this acceleration would require in terms of mass loss if it were due to natural cometary outgassing. The results were startling. To produce the observed non-gravitational acceleration, 3I Atlas would need to eject approximately 10 to 20% of its total mass near perihelion. For an object weighing 33 billion tons or more, this means ejecting several billion tons of material into space. Where is it? Where is the massive debris cloud that should surround an object losing billions of tons of mass? This question connects to the 10th anomaly, but it deserves attention here because the non-gravitational acceleration itself demands an explanation, and the most obvious natural explanation does not fit the observations. Cometary jets produce thrust most efficiently when they are collimated, focused in a specific direction rather than spreading out spherically. The images of 3I Atlas from early November show at least 7 distinct jets emanating from the nucleus in various directions. Some point toward the Sun, some point away, some angle off to the sides. When you have jets firing in many directions, the thrust forces partially cancel out. Only the net imbalance produces acceleration. This means that to achieve the observed non-gravitational acceleration with multiple opposing jets, the total mass ejection must be much larger than if you had a single well-aimed jet. The inefficiency of multi-directional outgassing compounds the mass loss problem. Professor Loeb calculated that with the observed jet geometry, 3I Atlas might need to lose 20 to 30% of its mass to produce the detected acceleration. This is an enormous fraction. Most comets lose a tiny percentage of their mass during a perihelion passage. Losing 20 to 30% would fundamentally alter the object's structure and possibly cause fragmentation, yet 3I Atlas appears intact. Post-perihelion images show a coherent nucleus with no obvious signs of breakup. The object survived its close solar encounter without disintegrating, despite allegedly losing a substantial fraction of its mass to space. There is a contradiction here that natural comet models struggle to resolve. Either the object is more massive than we think, meaning our size estimates are wrong and it is actually much larger, or the non-gravitational acceleration is not entirely due to cometary outgassing. If 3I Atlas is significantly larger than 5 to 10 kilometers, it would need to be 50 to 100 kilometers across to have enough mass that losing a few billion tons represents only a small fraction. But observations constrain the size, the brightness, the extent of the coma, the thermal emissions. All of these place upper limits on how large the nucleus can be. There is not enough observational wiggle room to hide a giant object. The alternative explanation is that the acceleration has a different source, something more efficient than random cometary jets. Directed thrust, deliberate maneuvering, active propulsion, these would produce acceleration with far less mass loss. A spacecraft firing thrusters does not need to lose billions of tons to change its velocity slightly. It needs to expel propellant at high speed, and even a small amount of propellant can produce significant delta V if the exhaust velocity is high enough. Professor Loeb has been careful to present this as a possibility, not a conclusion. He assigns a 30 to 40% probability that 3I Atlas is not entirely natural, based on the full suite of anomalies. The non-gravitational acceleration is a key part of this assessment because it is quantifiable, measurable, and difficult to explain with standard physics. Critics argue that we simply do not understand interstellar comets well enough to know what is normal. Perhaps they routinely lose larger fractions of mass than solar system comets. Perhaps their internal structure allows for more efficient outgassing. Perhaps the chemical composition we have already discussed, carbon dioxide dominance, unusual metals, creates conditions where high mass loss is natural. These arguments have merit but require assuming that interstellar comets are fundamentally different from solar system comets in multiple ways simultaneously. They must be chemically different, structurally different, and behaviourally different. At some point, invoking multiple special characteristics to explain an object becomes less parsimonious than considering alternative explanations. The timing of the acceleration detection is also notable. The non-gravitational component became apparent near perihelion, precisely when the object was closest to the Sun and when outgassing should be at maximum. This is consistent with cometary behaviour, but also consistent with a powered manoeuvre at perihelion, where such a manoeuvre would be most energetically efficient. The analysis from the Minor Planet Center and JPL will be refined over coming months as more observations accumulate. If the non-gravitational acceleration continues to be detected as 3I Atlas moves away from the Sun, that would be unusual. Natural cometary outgassing decreases rapidly with solar distance. If the acceleration persists or varies in ways uncorrelated with solar flux, it would suggest active control. There is also the question of direction. Non-gravitational acceleration has a vector, magnitude, and direction. For 3I Atlas, the acceleration appears to have components both in the direction of motion and perpendicular to it. This is consistent with asymmetric outgassing, but is also consistent with course correction, burns designed to maintain a specific trajectory. The statistical significance of the detection, 3.7 standard deviations, is below the gold standard, 5 sigma threshold used in particle physics, but well above the level where astronomers take results seriously. It is not a marginal detection. It is real, measurable, and requires explanation. Professor Loeb has pointed out that if 3I Atlas were a natural comet, we should eventually see it surrounded by a massive debris field, the gas and dust ejected during perihelion spreading out into space. This debris should be detectable by sensitive infrared telescopes like JWST and by spacecraft that might pass through it, like Europa Clipper did in early November. As of today, November 11th, reports of such a debris field remain ambiguous. Some observers report faint extended structure around the nucleus. Others see nothing beyond the expected coma. The absence of clear evidence for billions of tons of recently ejected material is itself an anomaly, the 10th and perhaps most damning piece of evidence that 3I Atlas is not behaving as comets behave. The physics of non-gravitational acceleration is not complicated. Force equals mass times acceleration. If you measure the acceleration and know the mass, you can calculate the force. If you assume the force comes from gas jets, you can calculate how much gas must be expelled and at what velocity. The math is straightforward. The results do not match the observations. This disconnect between prediction and observation is what science thrives on. When models and reality disagree, we have an opportunity to learn something new. Either our understanding of comets is incomplete, or 3I Atlas is not a comet in the traditional sense. Professor Loeb has been accused of jumping to conclusions, of letting his hypothesis about technological objects drive his interpretation of data. But when you read his papers, what you find is someone carefully presenting calculations and asking why the numbers do not add up. He is not inventing problems, he is documenting them. The non-gravitational acceleration of 3I Atlas is real. The mass loss required to explain it naturally is enormous. The debris cloud that should result from such mass loss is largely absent. These are facts, not speculation. How we interpret these facts, whether as gaps in our understanding of comet physics or as evidence of something more exotic, is where reasonable scientists can disagree. But we cannot dismiss the anomaly. The object is accelerating in ways that gravity alone does not explain, and the standard explanation for such acceleration does not fit the observations. Something about our understanding is wrong. Either comets are far stranger than we thought, or what we are calling a comet is something else entirely. The acceleration continues. The object moves through space, pushed by forces we detect but do not fully understand. And every measurement, every calculation, every attempt to model its behaviour brings us back to the same uncomfortable conclusion. 3I Atlas is not following the script. It is not behaving the way natural objects behave. And the most parsimonious explanation for an object that does not behave naturally is that it might not be natural. The missing debris cloud, the 10th anomaly. Professor Loeb has stated repeatedly that the coming weeks would reveal the 10th anomaly of 3I Atlas. As of November 11th, 2025, that prediction is coming true, and the implications are more profound than any of the previous 9 anomalies combined. If 3I Atlas is a natural comet that lost 10 to 20% of its mass during perihelion passage, if it ejected several billion tons of gas and dust to produce the observed non-gravitational acceleration, if it underwent the intense activity documented by multiple observatories, then there should be a massive debris cloud surrounding it. This cloud should contain at least 5 billion tons of material, possibly more, spread out over millions of kilometres of space. It should be impossible to miss. Infrared telescopes should see it glowing from absorbed solar radiation. Visible light telescopes should see it scattering sunlight. Spacecraft flying through the region should detect particle impacts. The debris cloud should be one of the most obvious features of 3I Atlas, a testament to its violent activity near the Sun. It is not there. Post-perihelion images from early November show 3I Atlas with a coma, certainly a fuzzy envelope of gas and dust typical of comets. But the scale and mass of this coma are far smaller than what the non-gravitational acceleration requires. Detailed photometry and spectroscopy suggest the coma contains perhaps tens or hundreds of millions of tons of material, not billions. Where are the other billions of tons? Where is the mass that was allegedly ejected to produce the rocket effect? It has vanished, or more accurately, it never appeared in the first place. This absence creates an impossible situation. The non-gravitational acceleration is real, detected with high confidence by multiple tracking stations. The acceleration requires massive outgassing if it is natural, but the debris that should result from such outgassing is not present in the expected quantities. The logic is ironclad, and one of the premises must be wrong. Either the non-gravitational acceleration is not due to cometary outgassing, or the mass estimates are drastically incorrect, or we are missing something fundamental about how material behaves in space. There are no comfortable explanations. Professor Loeb published his analysis of this paradox on November 4th, designating it as the 10th anomaly. He calculated the minimum mass loss required for natural outgassing to produce the observed acceleration, compared it to the observed coma mass, and found a discrepancy of more than an order of magnitude. The debris cloud is simply not there at the level it should be. Some researchers have suggested that perhaps the ejected material has already dispersed, spreading out so diffusely that it becomes undetectable. But this does not work temporally. 3I Atlas reached perihelion on October 29th. By early November, less than 2 weeks later, material ejected near the Sun should still be relatively concentrated, moving outward at typical cometary dust velocities of hundreds of meters per second. It takes months for a cometary debris cloud to disperse to the point of invisibility. Others have proposed that maybe the material was ejected at much higher velocities than normal, spreading out faster and becoming undetectable more quickly. But high ejection velocities require more energy, more force, more thrust. If anything, this makes the missing mass problem worse, not better, because it implies even more efficient propulsion than standard cometary jets provide. There is also the question of composition. If the ejected material were pure gas with no dust, it might be harder to detect. But spectroscopic observations clearly show dust in the coma, particles that scatter light and should be visible if present in large quantities. The dust-to-gas ratio appears normal for a comet, which means if billions of tons of gas were ejected, there should be hundreds of millions or billions of tons of dust accompanying it. The Europa Clipper spacecraft travelling toward Jupiter passed through the predicted location of 3I Atlas ion tail between October 30th and November 6th. This was a rare opportunity to directly sample material from an interstellar object. The spacecraft carries instruments sensitive to charged particles, ions and dust grains. If 3I Atlas had shed billions of tons of material into space, Europa Clipper should have flown through some of it. As of today, NASA has not released data from Europa Clipper regarding any encounter with 3I Atlas debris. This may be due to the government shutdown affecting data release timelines, or it may be due to the ongoing internal restructuring at JPL, or it may be because there was nothing significant to detect, no massive debris cloud, no ion tail dense enough to produce measurable signals. The ESA's JUICE spacecraft was positioned to observe 3I Atlas during early November from a vantage point on the opposite side of the Sun from Earth. JUICE has cameras, spectrometers, and particle detectors that could characterize a debris cloud if one existed. But the data from JUICE will not be transmitted to Earth until February 2026 due to the spacecraft's communication systems and distance from Earth. We will have to wait months to learn what JUICE saw. This communication delay is itself interesting. Why does JUICE, a flagship mission equipped with sophisticated instruments, require months to downlink data? The technical explanation involves antenna configurations and data rates, but the timing creates an information gap precisely when we most need observations of 3I Atlas. Amateur astronomers with modest telescopes have continued imaging 3I Atlas as it emerges from behind the Sun. Their images show a compact nucleus with a modest coma, exactly what you would expect from a small to medium-sized comet. They do not show the massive, extended debris field that should surround an object losing billions of tons of mass. Professional observatories with larger apertures and more sensitive detectors have attempted deep imaging to search for faint extended structures. Some report tentative detections of diffuse material at the limits of their sensitivity. Others see nothing beyond the normal coma. The results are ambiguous, but the absence of clear, unambiguous detection of a massive debris cloud is itself significant. Professor Loeb has pointed out that if the 10th anomaly holds up, if further observations continue to show no evidence for the expected debris cloud, then the natural comet hypothesis becomes untenable. You cannot have significant non-gravitational acceleration without mass loss, and you cannot have massive mass loss without a detectable debris cloud. The physics does not allow it. The alternative explanation is that the non-gravitational acceleration is produced by a propulsion system, thrusters or engines that expel small amounts of propellant at very high velocities. Rocket engines on spacecraft achieve high efficiency by accelerating exhaust to velocities measured in kilometers per second, not the meters per second typical of cometary jets. This allows large momentum changes with relatively small mass expenditure. If 3I Atlas were using such a system, it could produce the observed acceleration while losing only a small fraction of its mass, perhaps a few 100 million tons instead of several billion. This amount of mass loss would produce a coma consistent with observations, without requiring an enormous debris cloud. But this explanation requires accepting that 3I Atlas is artificial, that it is manoeuvring, that it has propulsion. It requires abandoning the natural comet hypothesis entirely and embracing the possibility that we are observing technology. The scientific community is deeply uncomfortable with this conclusion. It violates decades of experience with comets and asteroids. It implies the existence of extraterrestrial intelligence capable of interstellar travel. It forces us to reconsider our place in the universe and the likelihood that we are not alone. Yet the data does not care about our comfort. The non-gravitational acceleration is real. The missing debris cloud is real. The logical conclusion, however unsettling, is that standard cometary physics cannot explain 3I Atlas. Professor Loeb has emphasized that the 10th anomaly is not confirmed until we have more observations over coming weeks and months. If JWST or other major telescopes eventually detect the missing debris cloud, the anomaly disappears and 3I Atlas returns to being an unusually active but ultimately natural comet. If the debris cloud remains absent despite intensive searching, the case for technological origin becomes overwhelming. December the 19th, 2025 is the critical date. That is when 3I Atlas makes its closest approach to Earth, passing within 167 million miles of our planet. At that distance, our most powerful telescopes will have their best opportunity to observe the object in detail, to search for the debris cloud, to measure composition and structure, to look for any signs that might definitively answer the question of what this object is. Until then, we are left in uncertainty, watching an object that defies explanation, that accumulates anomalies faster than we can rationalize them. 10 anomalies. 10 separate observations that each individually strain natural explanations, and collectively create a pattern that is becoming impossible to ignore. The ecliptic alignment, the sunward jet, the extreme mass, the perfect timing, the industrial nickel, the bizarre polarization, the missing water, the blue brightening, the unexplained acceleration, and now the absent debris cloud. Each anomaly, taken alone, might be dismissed as an outlier, a statistical fluctuation, an edge case in the distribution of natural phenomena. But 10 anomalies, 10 separate independent observations that all point in the same direction. At what point do we stop invoking special pleading and start considering that maybe, just maybe, 3I Atlas is exactly what the data suggests it is? Professor Loeb has stated that his confidence in a non-natural origin is currently 30 to 40%, but that this estimate will be revised based on data from the coming months. If the debris cloud appears, his confidence will drop. If it remains absent, his confidence will rise, possibly to the point where the technological hypothesis becomes more probable than the natural one. We are living through a moment of profound uncertainty, watching an object from beyond our solar system as it performs a grand tour of our planetary neighbourhood, exhibiting behaviours that challenge everything we thought we knew about comets. The next few months will determine whether 3I Atlas goes down in history as an exotic but natural visitor, or as the object that forced humanity to confront the reality that we're not alone in the universe. The missing debris cloud is the key. It is the observation that cannot be explained away with exotic chemistry or unusual formation conditions. Either the mass is there, hidden somehow, or the acceleration is not due to natural outgassing. There is no middle ground, no comfortable compromise that lets us maintain our assumptions about what comets are and how they behave. 3I Atlas continues its journey, moving away from the Sun, approaching Earth, carrying with it the answer to questions we have asked for millennia. Are we alone? Is there intelligence beyond Earth? Has technology from another civilization entered our solar system? The 10th anomaly suggests the answer might be yes. The missing debris cloud, the absence of what should be there, is itself a presence, a signal, a message written in the language of physics that something about this object is fundamentally different from what we expect. And in science, when observations consistently contradict expectations, we have two choices. We can cling to our expectations and invent increasingly elaborate explanations for the discrepancies, or we can revise our expectations to match reality. The data from 3i Atlas is forcing that choice upon us, demanding that we either expand our understanding of natural phenomena or accept the possibility that not everything passing through our solar system is natural. The next chapter of this story will be written not by speculation but by observation, by telescopes pointing at a specific region of sky, by detectors searching for particles that should be there, by instruments measuring light and matter to determine what 3i Atlas truly is. Until those observations are complete, we wait, we watch, and we wonder whether the universe is about to reveal one of its most profound secrets. The 10th anomaly is real, the debris cloud is missing, and that absence speaks louder than any presence could.